68 tons of steel and composite armor, 3 people, sometimes 4, sealed inside a space smaller than a garden shed, breathing filtered air pumped in under pressure so that nothing from outside can leak past them. Around those people, and this is the part that does not sit easily once you know it, sits their own ammunition. Dozens of rounds, each one longer than a man's arm, each one holding a charge that turns a chemical reaction into a moving object at better than a mile a second. The tank is built to be struck. It will be found and it will be hit, and the question the engineers set themselves was never how to stop that. The question was, what happens in the half-second afterward, inside a metal box with the crew and the ammunition in the same sealed volume? The steel is not the thing that keeps those people alive when that half-second arrives. Something else is, and it is not what you would guess. Here is the assumption almost everyone carries about a tank, and it is wrong in a specific and interesting way. You look at the M1 Abrams and you see armor. You see the thickness of it, the angle of the turret, the sense that this is a thing built to absorb a blow and shrug it off, and the armor is real, and it is extraordinary, and we will come to it. But the armor is not the last line protecting the crew, because the most dangerous thing on the battlefield to an Abrams crew has never been the round coming toward them from outside. It is the ammunition already inside with them. A modern tank round does not need an attacker to end the people around it. If it cooks off inside a closed compartment, the crew does not survive the pressure, and no amount of frontal armor changes that, because the threat is already past the armor. It is sitting in the rack. So the engineering problem the Abrams solves is not really about keeping penetrators out. It is about what the tank does with its own stored energy at the moment something gets in. There are 4 systems that answer that problem, and all 4 are worth understanding. The way the ammunition is separated from the crew, the way the blast is given somewhere to go, the way the air the crew breathes is managed, and the way fire is caught before it spreads. 4 systems, and behind all 4, one person who has to close a door. We will take the era as it stands today, the tank in current service, and every figure here is drawn from the published and declassified record. If you find this kind of thing worth an hour of your attention, the channel is built entirely on it, so consider subscribing before we go inside. We start with the danger itself, because nothing that follows makes sense until you understand what the crew is actually sitting next to. Understand first what the ammunition is, because the word does the concept a disservice. A 120mm tank round is not a bullet made large. It is a sealed unit holding a propellant charge, and that charge exists to do one thing, which is to release an enormous quantity of energy in a controlled direction in a fraction of a second. Inside the gun, pointed down the barrel, that is exactly what you want. The energy goes where the engineering sends it. But the propellant does not know it is inside a gun. It carries the same energy whether it is in the breech or in the rack, and if it is ignited in the rack, by a fragment, by heat, by a penetrator that has found its way into the compartment, that energy releases in exactly the same way. It just releases in the wrong place, with no barrel to guide it, inside a sealed steel box with people in it. The military term for this is cook-off, and it is worth being precise about what it means. It does not mean a single round going off. It means the first round releasing enough heat to ignite the next, and the next, in a chain that takes a small part of a second to run through an entire rack. The pressure that builds inside a closed crew compartment when that happens is not survivable. This is the physics the whole design answers to, and it is why the placement of the ammunition matters more than almost anything else about the vehicle. Now hold on to one idea, because it reframes the problem. The overwhelming majority of tank crew losses across the history of armored warfare have not come from the incoming round punching through and striking a crewman. They have come from what that round set off once it was inside. The penetrator is the trigger. The ammunition is the thing that actually does the harm, which means a tank can be defeated and destroyed as a machine, and the crew can still walk away, if and only if the stored energy is sent somewhere other than through them. That distinction between losing the tank and losing the crew is the entire subject of this episode. Everyday intuition gets you close here. Think of a pot of oil on a stove with the lid clamped down hard. Heat it and it will build pressure until something gives, and where it gives is not your choice unless you built the pot to give in a chosen place. The Abrams is a pot built to give in a chosen place. That is the whole idea. And the next part is how they chose it. So here's the inversion, and it is the single thing most people do not know about how this tank is built. The crew is not protected from the ammunition by making the ammunition harder to hit. The crew is protected by accepting, in advance, that the ammunition will be hit, and by deciding ahead of time exactly where the explosion will be allowed to go. The main gun rounds are stored in a compartment in the rear of the turret in what is called the turret bustle, that box shape you can see projecting off the back of the turret in any photograph of the tank. That compartment is behind the crew and separated from them by a set of armored doors, and those doors are the hinge on which the entire survival concept turns. When the loader needs a round, the doors open, and here's a detail that tells you how seriously the design takes this. The doors are opened by the loader's knee, pressing a switch so that both of his hands stay on the round. They slide open only far enough and only long enough to pull one round, and then they close automatically. For all but a few seconds of a firing cycle, the crew and the ammunition are on opposite sides of armored steel. And once the doors reach the last fraction of an inch of closing, they cannot be stopped. That is deliberate. Now the roof of that ammunition compartment is not solid in the way the rest of the turret is. It is fitted with panels designed to fail. They are called blowout panels, and they are engineered to rupture at a specific pressure before the pressure inside the compartment can build to the level that would burst the walls inward toward the crew. So when a penetrator reaches the ammunition and the rounds cook off, the blast takes the path of least resistance, which the engineers have deliberately made the path straight up, out through the roof, into the open air. The flame and the gas and the pressure go skyward. The blast doors, closed, hold the line between that compartment and the crew. And this is not a theory that lives only in a test report. There are numerous documented instances, photographed and filmed, of Abrams tanks that have taken a catastrophic ammunition detonation. The entire bustle blown open, fire pouring vertically out of the roof, and the crew climbing out alive. The tank in those images is finished. It will not fight again. But the people are walking. Now think about why the pressure limit on those panels sits where it does. It is not set at the point where the crew would die. It is set far below that, at the point that comfortably guarantees the blast vents upward every time, with margin to spare. The design is not trying to keep the crew just barely alive. It is trying to make the lethal case impossible to reach. That is a stronger idea than survival. It is the removal of the failure mode. And the people who crew these tanks train around it as simple fact. The doctrine is explicit. The ammunition doors must be closed before the main gun is armed. It is not a suggestion. It is the rule that makes the rest of the geometry mean anything. Which raises the next question, because a panel in a roof is only as good as the structure it is set into, and the structure is where the passive protection really lives. Look at the shape of the turret, and you are looking at a set of decisions, none of them cosmetic. The Abrams turret is faceted, flat-planed, with the ammunition carried in that distinct box at the rear, and every part of that arrangement is doing a job. Start with the separation itself, because it is structural before it is procedural. The ammunition compartment is a walled steel enclosure that is, on the later models, effectively its own module, bolted to the turret rather than integral with it, so that when the panels do blow and the compartment walls take the shock, the whole unit can be replaced rather than the turret written off. The blowout panels sit on top and to the rear, angled so that whatever comes out of them is directed up and away, not across the deck where it could find another opening. Now the armor. The Abrams uses a composite arrangement, layers of steel and ceramic and open space packed into the frontal structure, and later a further element documented in the open literature. The inclusion of depleted uranium in the frontal array, chosen not for anything exotic but for its density. A given thickness of it stops more than the same thickness of steel. That is the whole reason it is there. It is heavy, and the tank is heavy because of it, nearly 68 tons, and that mass is not incidental. It is the physical cost of deciding that the crew compartment will be the best protected volume in the vehicle. But here is the thing the armor cannot do, and it is the same lesson as before from a different direction. Armor protects against what comes from outside. It does nothing about what is already inside, which is why the internal walls matter as much as the external ones. There are armored bulkheads between the crew and the fuel. The tank runs on a turbine engine that will burn almost anything you put in it, and it carries a great deal of that fuel, and between that fuel and the people is deliberate steel. Hold on to that detail. The bulkhead, between the crew and the fuel. It will matter later when we get to a night at a base in Texas. Count what is actually holding, from the crewman's seat outward. In front, the composite array. Behind, the closed blast doors and the ammunition module with its vented roof. Between him and the fuel, an armored bulkhead. Below and around, the hull structure. He is sitting inside a series of nested boxes, each one drawn to fail in a direction that is not toward him, and one of those boxes has a second job that has nothing to do with stopping anything. The crew compartment is sealed well enough to hold pressure, and it is held at a pressure slightly above the outside air. That was done so that in a contaminated environment, nothing can leak inward because the air is always trying to leak outward. The seal exists for the ammunition and the blast geometry, but that same seal, that same overpressure, is what makes it possible to control the air the crew breathes at all, which is the next system, and it turns out the air is a more interesting problem than the armor ever was. Here is where the obvious threat turns out to be the wrong one to worry about. Ask what is going to hurt a tank crew, and the mind goes to the incoming round, the penetrator, the thing coming in. But across a long day buttoned up inside a sealed steel compartment, the thing quietly working against the crew is the atmosphere itself. Fire the main gun and the breech, even with the fume extractor doing its work, releases combustion products into the compartment. Run the systems, the electronics, the hydraulics, the bodies of 3 or 4 working people, and the air inside a closed volume degrades. Add heat. A turbine engine throws off an enormous thermal signature. The compartment sits in the sun, the electronics run hot, and the temperature inside a closed tank in a desert can climb to a level that is not merely uncomfortable but genuinely dangerous to human function. The crew's judgment is the first thing to go, long before anything more dramatic, and a crew whose judgment is slipping is a crew that makes the small mistakes that the whole design cannot protect against. So the tank manages its air, bound up at that pressure seal we just described. The Abrams draws air off the turbine engine, an abundant supply because of the kind of engine it is, filters and conditions it, and pushes it into the crew compartment under pressure. This is the overpressure system, and its first stated job is protection against nuclear, biological, and chemical hazards. The overpressure means that in a contaminated environment, the crew are breathing clean, filtered air, and nothing from outside is finding its way in, because the pressure gradient runs the wrong way for it. And now the second function, the one that is not in the name. That same conditioned air is what keeps the crew and, just as importantly, the electronics from cooking. On the later models, an air conditioning capability was added into that same architecture, and part of the reason was the crew, but a large part of it was the targeting and thermal and computing systems, which fail in heat exactly the way any electronics fail in heat. The system that protects against a chemical attack is the same system that keeps the fire control computer alive in a Kuwaiti summer. One piece of engineering, 2 problems that look completely unrelated until you see they share a solution. Now walk the defense in layers from the sophisticated down to the crude, because the crude layer is the one that matters most. The overpressure and filtration is the sophisticated layer, and it depends on the engine running and the system working. Below that, the crew carry individual protective suits and masks, which do not depend on the vehicle at all. If the overpressure system is down, the masks still work because they need nothing from the tank. That is the pattern worth noticing across this whole machine. The most capable protection depends on power and systems. The protection that survives a total loss of everything is the one a person puts on with their own hands. The mask does not care whether the turbine is turning, and behind all of it is a rule set that governs what can be stored where and in what quantity, because the blast geometry we admired earlier has a limit that the crew has to respect. Store the wrong mix of rounds in the wrong place, too many of a type that carries its own high-explosive filler, and you can overwhelm the very blowout panels that are supposed to save you. So the protection is not only steel and pressure, it is also a set of loading rules that a crew has to follow every time, and a set of modern insensitive munitions, propellants, and explosives formulated specifically to be harder to set off in the first place. The hardest round to cook off is the one chemically designed not to. That combination, the vented compartment plus the ammunition that resists ignition plus the rules about what goes where, is what makes the geometry hold, and every part of it assumes something will still, eventually, go wrong. Which brings us to a night when it did, and not in a war. It was a Thursday in the spring of 2020 at Fort Hood in Texas, and there was no battle anywhere near it. An M1 Abrams belonging to an armored cavalry unit caught fire outside its own motor pool, in garrison, on home soil, doing nothing more dramatic than sitting where tanks sit. There are videos of it, taken by soldiers, the tank burning in the open with people standing well back. The initial account, the one that went into the investigation, pointed at a fuel leak that had not been dealt with. Remember the bulkhead. Remember the armored steel deliberately placed between the crew and a turbine engine's worth of fuel. The detail set down earlier with a note that it would matter. This is where it matters. A fuel fire in a tank is not a small event. The turbine will run on a range of fuels, and the vehicle carries a great deal of it. And a leak that finds an ignition source produces exactly the kind of fire that the internal architecture, the bulkheads, and the compartmentalization and the automatic suppression exists to contain and keep away from the crew and away from the ammunition. No one was lost. No one was seriously hurt. That is the first thing the Army said, and it is the thing that matters most for our purposes because it is the design working in the least glamorous possible circumstance. A maintenance state fire in a parking area rather than a hit in battle. But the investigation did not stop at the fire, and here's the part that shows how this audience's instinct for detail is the right instinct, because the Abrams frontal armor contains depleted uranium, and because depleted uranium, when it burns, can leave fine particulate that a person can breathe. The inquiry had to ask a second question that had nothing to do with flames. It had to ask whether the crew had been exposed to something the fire released from the armor itself. The material chosen for its density, the thing that makes the front of the tank stop what it stops, becomes, in a fire, a separate hazard that has to be investigated on its own terms. Nothing in that chain was exotic: a leak, a source, a fire, a material doing in an accident exactly what its physics say it will do. Ordinary things, assembled in one order, on an ordinary day, producing an event serious enough to investigate fully. That is the value of a case like this. Not the spectacle, but the demonstration that these systems are not there for the dramatic battlefield moment alone. They are there for the Thursday and the motor pool, and the reason no one was hurt is that the bulkhead and the suppression and the separation did on an ordinary day exactly what they were drawn to do. The change that comes out of an event like this is rarely a new invention. It is a tightening, a procedure around fuel system maintenance, checklist item, an inspection interval, which is the honest shape of how these machines get safer. Not by a breakthrough, but by someone writing down what went wrong so the next crew catches it first. Which leaves the part of the system that was never engineered because it could not be. Every layer we have described, the blast doors, the vented roof, the overpressure, the bulkheads, the suppression, does exactly what it was built to do and not one thing more. None of it decides. The blast doors do not know whether they are open or closed at the moment a penetrator arrives. The panel does not know it is venting. The suppression system, which triggers in a small fraction of a second, faster than a person could react, floods the compartment with an agent the instant it senses a flash. And here is a fact that captures the whole balance of the thing. That agent is itself not good to breathe, but it is chosen because what it prevents, an uncontrolled fire in a closed compartment, is far worse than the agent, and because the obvious cheap alternative would be lethal to the crew outright. Even the safety system is a managed trade. A lesser harm accepted to remove a greater one, and it runs automatically because no human nervous system is fast enough to be trusted with that decision. So the fast things are automatic, but the slow things, the things with seconds or minutes in them, still come back to a person. Someone has to have closed the blast doors before the gun was armed, every single time, because the doctrine says so and because the geometry is worthless if the door is open. Someone has to have stored the rounds in the right places and the right numbers, following the loading rules so the panels are not overwhelmed. Someone has to have noticed the fuel weep on the maintenance check, the thing that at Fort Hood apparently was not caught in time. Someone has to put the mask on. The crews train for this the way they train for gunnery, and that training is not an add-on to the engineering. It sits inside the architecture, in the same place as a relief valve, a designed response to a known failure mode, the failure mode in this case being an ordinary human being under heat and fatigue and time pressure forgetting one step, and the conditions work against them in ways that have nothing to do with any attacker. Buttoned up, the crew loses the world. No weather, no horizon, no variation. The same filtered air and the same instrument glow and the same noise hour after hour. The heat pressing in even with the conditioning running, the compartment barely larger than the people in it. That environment does something to human attention over a long day, and the design knows it, which is why so much of the protection was made automatic or passive, to take the slow-reacting, tiring human out of the loop wherever a machine could be trusted instead. But it could not be taken out of every loop. The honest pattern, the one the record shows again and again across armored vehicles, is that the serious events tend to trace back not to a failure of the steel, but to a missed indication or a skipped step, a door that should have been closed, a leak that should have been caught, a rule about loading that was bent because it was quicker. The machine is built so that the catastrophe cannot assemble itself out of any single mechanical failure. What it cannot do is build itself around the one component that has no backup, no redundancy, no automatic override, which is the attention of the person doing the job. So count the 4 systems again, quickly, the way they actually stack. The ammunition is separated from the crew behind armored doors that stay closed for all but a few seconds. The blast, when it comes, is given a path straight up through panels built to fail before the crew compartment can. The air is sealed, pressurized, and conditioned, protecting the crew from contamination and heat with the same architecture. And fire is caught in a fraction of a second by a system that accepts a small harm to prevent a total one. 4 systems, and behind all of them the 5th thing we named at the start, which now has a face. It is the crew member who closes the door. Go back to the image we opened with. The crew sealed in a space smaller than a shed with their own ammunition around them, and you see it differently now. That is not a reckless arrangement. It is the most carefully reasoned arrangement on the whole battlefield, a design that starts by admitting it will be hit and spends 68 tons making sure that when it is, the energy goes anywhere but through the people. The tank is the thing permitted to be lost, so that the crew is the thing that is not. And the strange, quiet truth of it is that all of that engineering, all of that steel and geometry and chemistry comes down in the end to whether one tired person in a hot box remembered to press a switch with their knee. If you want to keep looking inside machines like this one, the kind almost no one is allowed to climb into, that is the whole reason this channel exists, so subscribe and stay with it. The next one goes underneath the warship, into the compartment where a naval reactor makes steam, without ever being allowed to stop. And the strangest part is what the crew has to do to shut it down when the rules say it must never shut down at all. And here's a question for the comments while you think about this one. If the entire design accepts that the tank itself will be destroyed to save the people inside it, is that a tank built to win or a tank built to survive losing, and are those actually the same thing? There's a good argument on both sides, and I would like to read yours. This video is for educational purposes only. It draws on published engineering literature, declassified documentation, manufacturer and service publications, and investigated peacetime incident reports. Where a figure is an outside estimate or has never been released, this is stated, and where practice varies between services or jurisdictions, this is noted. Nothing in this video is operational guidance.